Hi everyone, and welcome to today's webinar, There's No Such Thing as Non-Model-Based Systems Engineering, presented by Zane Scott. My name is Donna Long, and I will be your host during today's webinar. Over nearly 40 years, Zane has built his professional skills and expertise through a multifaceted career. As the Vice President for Professional Services at Vitek Corporation, he is responsible for leading the delivery of training and consulting services, as well as the development of educational and intellectual collateral. A frequent blogger and speaker on systems engineering topics, Zane co-authored Vitek's Primer for Model-Based Systems Engineering with David Long, Vitek's president. Active in the International Council on Systems Engineering, Zane has served as the chair of the Corporate Advisory Board and a member of the Board of Directors. He has delivered the SE 101 tutorial for the INCOSE International Symposium for 3 years, 2013 through 2015, won a Best Paper Award with Dave Walden of Sysnovation at IS 2016, and teaches the fundamentals of systems engineering for Vitek with other companies and INCOSE chapters. Zane comes to the world of systems engineering with a diverse and interesting background, having been a trial attorney, hostage crisis negotiator, labor management facilitator, and mediator. He is a member of the inaugural cohort of INCOSE's Institute for Technical Leadership and is particularly interested in developing leadership skills among engineers and other technical professionals. Before joining Vitek, Zane worked as a senior consultant and process analyst, assisting government and industry clients in implementing and managing organizational change. Before Zane gets started, I have just a few housekeeping items. We will be answering questions at the end of the webinar. Please send your questions in as soon as you think of them through the question tab on the webinar control panel. Zane will answer as many questions as he can today, but if we do not get to your question, we will reach out to you after the webinar. The webinar is being recorded. If you experience connection problems during the live presentation, a recording will be made available within 1 business day. The recording will be published to Vitek's webinar archive located on our website. At the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you would like to see covered in future webinars. Now I'm going to turn the presentation over to Zane. Welcome.
Thanks, Donna, and welcome everybody. Thanks for being with us this morning. I hope that you'll find it productive and interesting along the way. The title is intentionally provocative. There's no such thing as non-model-based systems engineering. All systems engineering is model-based. The reason for this is clear once you see what's involved, and it makes good sense because there's no human endeavor that's really not model-based, a human endeavor that does not turn on the models that we have in our heads and in our lives. We use models as human beings as we're hardwired to do intuitively. I want to illustrate one of the ways that we use it with a little story about 4 brothers. These 4 brothers had gone to college and become successful and prosperous, and one night they were having dinner together. As they ate, they were discussing gifts that they were able to give their elderly mother who lived far away in a distant city. The first brother said, "Now I'm having a big house built for Mama." And the second one said, "Well, I'm going to install a $100,000 theater inside the house." The third one said, "I'm having my Mercedes dealer deliver a $130,000 S-Class coupe to her." The fourth said, "You know how Mama loves reading the Bible, and you know she can't read anymore because she can't see very well. Well, I met this preacher who told me about a parrot that can recite the entire Bible. It took 20 preachers 12 years to teach him that. I had to pledge to contribute $100,000 a year for 20 years to the church, but it was worth it. Mama just has to name the chapter and the verse that she wants to hear, and the parrot will recite it." The other brothers were suitably impressed. After the holidays and the gift giving were over, Mama sent out her thank you notes. To the first brother, she wrote, "Milton, the house you built is so huge. I live in only one room, but I have to clean the whole house. Thanks anyway." To the second, she wrote, "Marvin, I am too old to travel. I stay home. I have my groceries delivered, so I never use the Mercedes, but the thought was good. Thanks." To the third, she wrote, "Michael, you gave me an expensive theater with Dolby sound. It could hold 50 people, but all of my friends are dead. I've lost my hearing and I'm nearly blind, and so I never get to use it. Thank you for the gesture just the same." But to the fourth, she wrote, "Dearest Melvin, you were the only son to have the good sense to give a little thought to your gift for me. The chicken was delicious. Thank you." Now, this is funny to the extent that you thought it was funny because of the twist that's involved. And that's the way humor works, all the way from slapstick with pratfalls, all the way through to subtle jokes that it takes a few minutes to get. The humor is based on a violation of the way that we think the world works. It works because we build models of how the world works in our heads. And the stories, the humor, the jokes put a twist on those models and show us something unexpected. And the more unexpected what we're shown is, the funnier it is. That's how we're hardwired to use models. We construct the models in our mind. So let's dive in and start off by talking about how we use models. Warren Buffett's investment and intellectual partner, Charlie Munger, has said that you really can't know anything if you just remember isolated facts and try to bang them back. If the facts don't hang together in a latticework of theory, then you don't have them in a usable form. You've got to have models in your head, and you've got to array your experience, both vicarious and direct, on this latticework of models. You've got to hang experience on a latticework of models in your head. And that's true for all of us. In some way, and some are better organized than others, we develop models in our heads, and then we take the experiences that we have, the observations that we make, and we fit those into the models and into the latticework that we have in our heads. The latticework provides the same function that a card catalog in the Dewey Decimal System and shelving do in a library. Just as those systems operate to organize the books in ways that we can lay our hands on them. You can go into the library looking for something and be directed by the organization of the card catalog, and the shelving can be directed right to what you're looking for. So the lattice work of the Dewey Decimal model of organizing the library is what makes the difference between a library and just a pile of books. And the models in our head are what make the difference between a coherent experience of the world and just a jumble of facts in our heads. So the first way we use models is to think. A second way that we use models is to communicate. In communication, the purpose, no matter what the method we're using, is to transfer information from a sender to a receiver. If it's two-way communication, then the purpose is to transfer the information from the sender to the receiver, and then the receiver becomes a sender and transfers information back in the other direction. But the object of the communication is always trying to align or match the models in our heads, the models of whatever it is that we're discussing. We're trying to get aligned in our minds so that we're essentially seeing the same pictures or conceiving of the same concepts. Our models can become impediments to communication as well. If we start out with two different models of the same kind of concept and begin to communicate, one of us communicating out of one model and the other one communicating out of another model can lead to some often entertaining and sometimes costly errors in the communication. So not having the models in alignment can become a difficulty or an impediment to our communication. An exercise that I would do live with you if this were an in-person presentation is an exercise around the word horse. I would ask everybody to shut their eyes and to think about the word horse, to visualize in their minds what the word horse means to them. Now, the response to that is that some people would think of a white horse, and some people would think of a brown horse. Some people would think of a black horse, and other people would think of other different kinds of horses, a pinto or a dappled gray or whatever kind of horse comes to your mind in your horse model. And so as we think of those, then I have people raise their hands, keeping their eyes closed. Who thought of a white horse? Who thought of a brown horse? Who thought of a black horse? Who thought of any other kind of horse? And we get a portion of the group raising their hands for any one of those models. So that means that our model of a horse is in general alignment. Everybody thinks of four legs, a mane, and a tail. But not everybody thinks of the same color. Can that matter? Can that become an impediment? If we have different models of a horse, we're probably not far off on the concept of horse itself, but if color is going to matter, the color and type of horse is going to matter, then that can become a problem. For instance, if our purpose was to come up with a team of matched Clydesdales to pull a wagon, then visions of a model of a white horse. Some people are looking for a white horse to pull the wagon, others are looking for a brown horse, others are looking for a black horse. It becomes difficult to come up with a matched team because the models of what we're looking for are different in our heads. This is a very simplistic example of what happens with models when they remain totally in our heads. The way around that is to surface the model. We can get this out through multiple rounds of communication back and forth and maybe get to the point where we're pretty much on target. We could probably get to the matched team resolution that way. But when we start dealing with highly complex models, like we deal with in the area of systems engineering, the solution to the potential impediments of different models in our heads is going to have to be surfacing that model, most often in a tool and in a way that we can all see and work on and come to some agreement about. So as we begin to talk about how we might surface the model and how the models that we have in our heads can be put out into a tool and communicate, I think it's useful to return to the definition of a model. What exactly do we mean by a model in this discussion? Well, a model is a limited representation of a particular reality. The emphasis here is on the word limited. That's the $64,000 question, because the question is going to become, how limited do we mean? You've heard the saying, a map is not the actual territory. So if we have a map, we have some sort of a model of a territory, but we don't have the territory itself. On the left, you see a satellite photograph of the Washington, D.C. metropolitan area with some of the place names labels put on there. Some of the roads are highlighted. You can see network of roads. You can see political geographic boundaries on the map. But this is not the territory. So for instance, you can't experience the direction and speed of the wind. You can experience the noise levels in different parts of this model. So it's not a complete model of the territory, but it's a model that might be useful in some senses. On the right, we have an even more limited model of the Washington, D.C. area. It's more limited than the map that's on the left. It portrays the metro system and the stops along the metro system in D.C. So this is a much more limited depiction of the area. Now we'll talk more about this in just a few minutes. One caveat here is that sometimes we become so ingrained with the models that we tend to confuse them with reality. So anybody who has become steeped in Myers-Briggs and has encountered others who are steeped into it, you've heard things like, I am an INFJ, or for somebody who doesn't understand Myers-Briggs, maybe they think they're an ESPN. But in any case, when somebody says, I am an INFJ, which is an initialism that symbolizes a particular personality type, the initialism and the personality type are simply a model of one category of personalities. So no person is an INFJ. A person is a person. You are a person, I am a person, our personalities are our own. They may be more or less well described by a category in the Myers-Briggs system, but we are not INFJs or any of the other of the letter combinations possible with Myers-Briggs. The model never becomes reality, and that's very important. George E.P. is quoted a lot, and the cute part of his quote is, all models are wrong, but some are useful. What he's talking about there is the truth of what we were just talking about, that representations are not reality. So in the sense that models are a limited representation, they're going to be wrong by definition. So that's the first part of Box's quote, but that's not all he said. The really powerful piece of what he said and the really helpful piece of what he says goes beyond the reminder that models are limited representations and are not reality, and goes to the point of saying the practical question is, how wrong do they have to be to not be useful? And that is the main question that we're going to deal with. We're going to discuss how wrong a model needs in order to not be useful. To illustrate that, let's talk about our friend the farmer. The farmer's having a problem. The milk production in his dairy herd has declined to the point where he's not able to make money. And he's tried everything he knows. He's switched the pastures, he's rotated them in the fields where they graze, he's changed the food that he gives them at milking time, he's altered the circumstances, he's played music in the milking barn, all sorts of things to try to improve the milk production, and he can't do it. So in thinking about how to solve the problem, he thinks, you know, the smartest person I know lives down the road here, and she's an engineer. Maybe I'll ask her to come over and see if she can help me with my problem. So he invites her over, and she comes over, and after listening to the farmer's description, she says, yeah, I think I can help. So off she goes to help. She goes away to think about the problem and try to come up with a solution for the farmer. 2 weeks pass, and here she comes back up the road again. This time, she thinks she has an answer. The farmer, of course, is anxious to know what she thinks, so he asks her, "What do you think? Can you describe a solution for me?" And she says, "Well, first we assume a perfectly spherical cow with milk homogeneously distributed throughout." Now, she, in the great tradition of physicists and mathematicians, is beginning by making some assumptions. And the issue is going to be, do her assumptions and her abstraction of the model of the cow, because the farmer's cows are not perfectly spherical and milk is not distributed throughout, are those assumptions going to matter? Are they going to result in a useful model, or are they going to result in a model that's not to be used? So when we look at this, what we're seeing is a fundamental principle that shows us that as we increase the limitations in our model, or increase the level of abstraction in this case, which limits the model, the usefulness of the model will decline. So the more abstract or the more limited the model is, the less useful it will be in describing the reality. But it does not decline in a straight line, regular fashion, because there is a point with all models that we get to where the usefulness goes to zero. Models on the other side of that point may be useful to one degree or another, and models that are on the right side of that point are going to not be useful to us at all. And that point is determined by the purpose that we're going to put the model to. So the purpose for which we're making the model determines the point at which the limitations will cause it not to be useful. Once the limitations impede the purpose for which we're using the model's no longer useful to us. So if the spherical cow with milk homogeneously distributed throughout is too abstract for the farmer to be able to use it to analyze how he can increase the milk production, then her model is not going to be useful. But if that's not too limiting, if the farmer can still figure out a practical solution to the problem, which is the reason why we would use the model, then the model will be useful. So let's go back to our map of the metro. The model is wrong, like E.P. Box points out. It's limited. In fact, it's very limited. It's not to scale, so you can't tell anything geographic from this model. The points, the stations don't line up with each other in a geographic sense, so we can't tell where they are related geographically. If we took an aerial photograph and plotted where these subway stations are on the physical map, they're not going to be in straight lines, and they're not going to be as equidistant one from the other as they are. Anybody who's ridden the metro knows that these stations, some are further apart than others, so they don't occur that regularly. But these stops are on here in order. All of the stops on the system are here. Some are just regular stations, and some are marked as transfer stations, so you know that you can get to one or even two other lines at some of the stations. So if its intended use is to tell us where we are in relation to where we want to be and how to get there, then the model's useful. So if you want to know how to get from Union Station to board the orange line to go east to New Carrollton, then you know that what you need to do is you need to go in the Shady Grove direction, 3 stops to the transfer station at Metro Center, where you can transfer to the orange line and go in the New Carrollton direction to your destination. So this is a very useful model in that sense, a very useful depiction of the metro system. And in fact, this is the depiction that you see on the wall when you get on board the metro car and look around. You'll see one of these that's there for your reference about how many stops you need to go and where you need to get on and off and where you need to transfer. So yes, it's useful, but its usefulness is determined by its purpose. And given the purpose that it's made for, this is a useful model of the metro system. So what is a system model in the sense that we use it in systems engineering? Well, this is the new INCOSE definition of a system. A system is an arrangement of parts or elements that together exhibit behavior or meaning that the individual constituents do not. Almost any definition of system that you come in contact with will include these 3 elements. First, any system has to be an arrangement. In other words, things have to be in relationship to one another. And it must include parts or elements. So the system has individual parts or elements which are held together in the arrangement of the system in relationship to each other. And then that arrangement of parts or elements will exhibit behavior or meaning that the individual constituents do not. Now, that's going to have some implications for us. First is that in order to see a system or a model of a system, we have to be able to see all the elements and all the relationships. We can't see the system by taking it apart. So if we want to know something about this digital camera, we can't look at the parts of a digital camera neatly spread out on a cloth and get any idea of what the system will do and how it functions. We have to see them put together in full relationship in order to understand their behavior. Robert Edson, who now works for MITRE, wrote a book several years ago called Systems Thinking Applied. It's a primer that's freely available online, and I would encourage you to take a look at it, if not download it. I have it downloaded and I refer to it frequently to align my thinking about systems and my view of systems thinking. The second thing that Edson says about the process of system thinking is that it is a process. It's ordered. It's a methodical approach to understanding problem situations and identifying solutions to those problems. So we first take a systems view, which is systemic, and then we follow a systematic process in order to conduct systems thinking. That's because we can run into problems. Fritjof Capra, and if you're of a certain age, you'll recall that this is the guy who in the 70s came out with a book that was very popular at the time called The Tao of Physics. He was a particle physicist at that time who was looking at the principles of physics as compared to the principles of some Eastern religions. That quest led him ultimately into the study of systems, and from there he has migrated into the field of ecobiology and the study of natural systems as well as man-made systems. But Capra has a warning for us. This comes from his book. He's written several books, but the one, The Systems View of Life, is a really good treatise on systems and systems thinking. But he points out in that book that the properties of a system are properties of the whole. None of the parts have those properties. they only arise from the interaction and relationship among the parts, which means that you can't just aggregate the parts up and have the system, the view of the system, because a bucket of parts does not have the properties of a system assembled from those parts. And then what I think is the most important sentence in that whole book, he says, these properties are destroyed when the system is dissected, either physically or theoretically. In other words, take it apart in building it or take it apart as we think about it into isolated elements. What he's talking about here is the principle that if we deconstruct a system, then we lose the properties of the system. So what does this have to do with our models? Well, we need to think about what makes a system model useful. That takes us back to the discussion of where's the point where the usefulness of a model falls off. It falls off at the point where the model can no longer fulfill its purpose. Well, what's the purpose of a system model? The purpose of the system model is to help systems engineers make predictions as to whether a specific design is going to satisfy the stakeholder needs. In order to know that, we need to know what behaviors are going to be manifest by the system. So we need to take a look at the whole system and see the behaviors, including the emergent behaviors that will come from that particular arrangement of parts and elements in those particular relationships, and ask ourselves, are the properties of that system going to satisfy the needs of the stakeholders? So to be useful, the system model has to help the systems engineers, make that prediction. And in order to make that prediction, the systems engineers have to know, number one, how will this design behave when it's put together? And number two, is that going to meet the stakeholders' needs? That's the essence of systems engineering. And that's the purpose that the system model has to serve. Now, what are the characteristics of a systems model then? First and foremost, it has to offer us a system view. We have to be able to see the system in full relationship, or we're not going to be able to understand what is going to come from that system. The system model needs to be complete and it needs to be consistent. So it needs to have all the elements that are necessary. It needs to have all of the ways that those elements relate to each other. And it needs to be consistent in its structure. To be useful, that system model has to help us making the prediction of systems engineering. It has to answer those two questions. How will the design behave? And will that meet the stakeholders' needs? If it doesn't, the model's not useful. So it has to have all of the characteristics necessary to help make that prediction. So how do we make our systems models useful? Well, the first thing we'll talk about is the full systems view and the completeness of the model. We know that the system, the design behavior, is going to emerge from the interactions and relationships of the system's elements. So to predict what the behavior must be, we have to see the elements in full relationship. How can we be assured that we have all of the necessary elements and that we know what those relationships are? We know what the possibilities are for the relationships. Well, we think about what it takes to make a model complete. What does it take to make a system model complete? What are the elements that we're going to need? We know typically any systems engineer knows that we're going to need requirements to show us what the stakeholder needs are. We're going to need the requirements that develop later on. We're going to need functions. We're going to need components. There's a wide variety of elements that we're going to need. And then we're going to need to be able to relate them in all of the ways that are possible and that will occur in the system. So we have to have a big variety of relationships. The elements, the relationships, the attributes all go together in the way that we think about constructing a model. That's expressed in a meta model. Now the meta model, which you see here, is the meta model that Vitek has developed and used and refined over several decades in order to assure ourselves that we have a complete model with all of the relationships in full and fully described. Now, when we instantiate that meta model, our thinking about the way that we make the models into a database, we refer to that as a schema. So the nomenclature is that the meta model is expressed in the database as a schema. Our models are then laid into that schema, and we need to be able to use that to provide a clear systems view, because if we don't, then we're not going to have the ability to predict the behavior of the system that we're modeling. So we need to avoid not having the clear view. We need to have all of the elements possible, all of the relationships, all of the attributes, all of them in full relationship to each other, expressed in our model. Now, what kinds of issues can cause us problems along the way? One that's very commonly caused is the issue, the viewpoint that we can do this by having several models, many models. We can do this by putting our models into several different tools. But what winds up from that is that the model becomes fragmented. We don't have a complete systems model in any tool. We don't have a complete systems model in any one of the models. What that means is that they can't possibly be in full relationship. There's no one place that we can go to see them in full relationship to each other. What we've done when we do this is that we've taken the real residence of the model and moved it back into the designer's head. So the designer is allocating portions of the information to different tools or different models. And that's coming out of the model in the designer's head. And we now no longer have it surfaced. We don't have a disciplined way that we can keep track of its completeness and consistency. We have torn it apart. And when we do that, Capra warns us that the properties are destroyed when we dissect it, in this case theoretically, into isolated elements or even isolated groups of elements. Another fallacy that's fairly common is if I can make enough views of the model, then I can aggregate those views and that'll sum up to a model. That's simply not the case. Once again, to the extent that it exists, it only exists in the minds of the people making the views. And so if you have multiple view makers, you may have multiple models in the heads of those view makers. And you no longer have any way of using a tool to provide an overarching discipline to assure you of completeness and consistency. The model is not integrated, just as when we had multiple tools or multiple models. The model is not integrated together in these multiple views. And once again, Capra's warning applies. So when we specify that we're going to have several views, even if those are several good views, even if there's 9 of them or there are many of them, if all we have are views, we don't yet have a systems model that we can use to make the predictions we need to make. Another issue is that we have to be careful of standards. Standards can be a good idea. A standard way of communicating is a good idea. The problem with standards comes when we begin to hone in on some particular way of communicating or representing or building our models, if that is arcane. And by that I mean it's confined to a specific or limited group of people. So for instance, if we were to standardize on Egyptian hieroglyphics, and I realize that nobody would ever attempt to construct or communicate models using Egyptian hieroglyphics. But if we were adopting that as a standard way of communication, then we'd be good as long as we were just dealing with ancient Egyptians. If you want to expand your audience beyond that to others who are bumfuzzled by hieroglyphics, then we begin to have problems. So how does that apply to us? What do I mean in practical terms? Well, let's say in practical terms, just for argument's sake, that we decided to standardize on views and expressions and representations that come from the world of software. So we adopt as a standard a set of representations that comes from UML and SysML. And we have those representations, and we don't have other representations. So if I output my model into diagrams that are constructed according to that standard, and I happen to be trying to model the throughput of an emergency room and operating room suites for a hospital, if I take those software representations to the hospital administrator, they're going to be confused. They're not going to resonate with the representations. And I'm going to be faced with conducting a class in the language. So it would be as if I attempted to lecture in English to a group of people who were a part of another culture and another language. I would be faced with either teaching them English or adapting other ways of communicating to them that fit with their language and culture. So when we limit our expressions to an arcane set, we limit the audience that we can talk to. And we know in looking at systems engineering that it's not just the software world, and actually it's not just the traditional systems engineering world that can benefit from systems engineering, but it's hospital administrators, it's policymakers, it's all kinds of people who don't necessarily identify with a very limited set of views and representations. The other issue that comes up is the issue of oversimplification. Often this is done in the name of accessibility. The most accessible version of the English language that most of us have ever seen was the version we used to learn to read. For those of us, again, of a certain age, and I'm of that age, we learned out of the Dick and Jane readers. So Dick and Jane had a dog, and the dog's name was Spot. And so we read sentences like, "See Spot run." Now that English, the constructions and the limited vocabulary are very accessible. They're so accessible that beginning readers can learn from them. That works in terms of describing things as long as you only have one dog. His name is Spot, and all he ever does is run. But if poor old Spot should get old and develop hip dysplasia and have to go to the vet for an operation to correct it, you're going to be up the creek in terms of trying to describe the complexities of Spot's malady and the cures, therefore, in this accessible, limited vocabulary and constructions. So when we oversimplify, we also lose our ability to communicate about complex subjects, to solve complex problems with complex solutions. And as we all know, that we are facing a complex world, dealing in complex systems, and that the complexity is magnifying every day. So what happens with all of these issues is that we get to the point where our models are not useful, where the usefulness just simply drops off. And it breaks apart our systems and our ability to communicate it. We can no longer see the system because it's broken apart. We can't think in an orderly and disciplined way about complex systems and all of their complexity. We can't communicate the complexity of our problems and their solutions. And the bottom line is we can't make the predictions that we need to make. So what are our takeaways from this discussion? Well, first, we've learned that models help us think and communicate. We use them for both purposes. We also learned that to think about systems, we have to be able to see those systems in whole and not in parts. It's not helpful to break the systems apart because we need to make predictions about possible solutions. So we need to see the system solutions that we're crafting and considering in the full system view. And we need to communicate our ideas and findings and conclusions to a variety of others. We have a variety of stakeholders who do come from the software background, who do resonate. We need to be able to communicate with them in a way that they resonate. We need to be able to communicate with those who come from the world of business and flowcharts. We need to resonate in a world of those who come from disciplines like healthcare delivery, who can benefit from the systems engineering tools and purposes. The lessons that we learn here are that the wider the audience, the wider the vocabulary we need. So for goodness sakes, don't constrict our vocabulary, and especially don't constrict it by adopting standards that define the limits of our communication. That wide audience also needs clarity, so don't confuse it with arcane kinds of expressions. Describing complex systems and subjects needs a rich vocabulary, so don't oversimplify it. Don't lose the ability to describe the complexity. And a system needs to be seen in whole in order to be understood. So please don't fragment the system view. Particularly, don't fragment it with multiple tools for any given system model, and don't fragment it with views without a database behind them, underpinning them. I've enjoyed the opportunity to be with you and spend time with you. I look forward to your questions. My contact data is here, and feel free to contact me and extend the discussion at any point. So, Donna, do we have questions?
Thank you, Zane. We do have a few questions, thanks to our participants. I encourage you to join the discussion now and submit your questions using your webinar control panel. Our first question is from Corey. Are you saying that views should be chosen based on the audience and not the preferences of the preparer of the view?
When we choose views, when we're representing our design, we do need to choose those views based on who the audience is. So a person with a business background is going to more easily understand an enhanced functional flow block diagram than an activity diagram. The reason is that the activity diagram contains things that they're not going to understand, but the functional flow block diagram is going to look to them like the business flow charts that they use every day. So we use those kinds of considerations in choosing a view. But hopefully you will all work with tools that allow you to input information about the design that you're making, about the model that you're crafting through constructing representations in the tool. So there's an inflow of information as well as an outflow of information. And it's important for the tool to provide for the kinds of people who will be inputting information as well. So in that sense, I suppose you would call the sources of the information that are putting it in through constructing views the audience. And in that sense, you should always consider the audience. But whether inflow or outflow, it's going to be the consumer of the view, the person who's using the view for a purpose who needs to be considered.
Okay. So our next question is from Josh. Why can't I aggregate the information from a requirements tool, an architecture tool, and a set of functional charts?
Well, that's the multiple tools fallacy, multiple models fallacy. The problem is that you're not really aggregating them any place except in our heads. And all of a sudden, we have now taken on the task of mentally conceiving of a complex solution to a complex problem. So now the problems that are generated are that others can't see the exact model that we have in our heads. So our communication may break down as we attempt to communicate what's in our heads. We can't count on the fragmented models to represent everything about the systems that we're seeing in our heads. And we have no disciplined way. The discipline that's imposed by the meta model, the schema, and the database that form the framework cannot tell us where what's in our heads is incomplete and can't tell us where what's in our heads is inconsistent. So we lose the bulk of the power of the tool when we attempt to aggregate into a model in our heads.
Okay. So our last question so far is a question from Sarah. How do you know if you have a complete model?
Well, the flippant answer is, for me, I know that I have a complete model when my tool tells me it's complete. When I use Genesis, for example, the tool tracks it and tells me that it's complete. So when I begin to verify, for instance, I can look at my model and choose the views designed for the purpose of showing me whether or not I've got all my requirements satisfied with functions in the tool. So is there a function that works to satisfy this requirement? And are all my functions performed by the physical architecture? So I can look for orphans in that whole structure as I do my verification process. And there's a completeness check that's applied by the tool. And that's what I mean by discipline and rigor that we gain when we start using the tool that's grounded in a proven meta model, a proven schema, because it tells me whether or not I'm complete.
All right. Thanks, Zane. That wraps up the final Q&A for today's presentation. If you have any other questions or comments, don't hesitate to send Zane an email. His email address is on the screen. He would be happy to hear from you with any inquiries you may have. Thank you so much for coming today. Please join us for our first live online town hall scheduled for next week, Thursday, May 28th. To register, there is a link on our website. Remember that at the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you would like to see covered in future webinars. That's all for today. Once again, thank you for joining us and have a wonderful day.
Thanks.